Okay, welcome back everybody. Okay, so let me just complete some things that I left in the morning. So morning we were seeing about this BIs being 0, right? If there is no odd cycle in the graph, then we know what the coefficients are going to be, right? Suppose there is an odd cycle, can we count how many are there? So suppose it is there means what? Obviously my say B3 is non-zero. If suppose I want to see how many triangles are there, then can I pull out the information from my polynomial? That is the question. So how many will it be there? B3 by 2, right? Why? Because in this part, if you see here, this 2 power ch, that there we are counting it, we are double counting every cycle, right? One for the positive orientation and negative orientation kind of. So every time if there is a cycle, we will be doing a double count, and obviously the C1H is not going to exist, right, because there is no edge in odd cycle, I mean components as edge as component is not going to exist in our H. So only thing is we will have this, only thing is we will have this 2 power ch coming into picture. So for any odd cycle, if it exists, okay, so this was the case where we saw if it does not exist, then we know it is 0. So if odd cycle exists, then the number of odd cycles, say of particular order, say of order k, if we are of order say 2k plus 1 if I am looking at, or say let me use some other alphabet, say 2p plus 1, then it is going to be nothing but negative of this coefficient C 2p plus 1, sorry, B 2p plus 1 by 2, right, it is half of that count. As we have made a double count, it is going to be just half of this, right. And coming back to this theorem, is everybody clear with how the equivalence works? Like how 1 implies 2, 2 implies 3, or the other way around, it is like 1 if and only if 2. So we have seen one way, obviously when G is bipartite, we have shown all these things will hold, right, 1 implies 2 and 1 implies 3 we have seen, right. So what about 2 and 3? That is, if we know about the characteristic polynomial has all the odd coefficients to be 0, this B2k plus 1s to be 0, then what can we say about the eigenvalues? Or knowing that eigenvalues are this pattern, then can I conclude that the characteristic polynomial will be like this? I mean, it is a very subtle detail that we need to just fill in the gap here, okay. So we have seen already 1 implies 3, if G is bipartite, we have seen how the eigenvalues are going to be present in the graph, right, and we have also seen that 2 implies 1 we have seen, right, that if your odd B2 2k plus 1 is 0, then we know there is no odd cycle, that means G is bipartite, right. So my question now is, how do I connect these 3 and 2? If I show the cycle will be completed if I show 3 implies 2, right, we have shown 1 implies 3 and 2 implies 1. So in between 3 and 2 we need to show some equivalence, right, otherwise our this equivalence claim will not be complete. So how can I show that this 3 implies 2? I mean, of course I can show that, can you show that? So given the fact that lambda and minus lambda is sitting there, can I show that the characteristic polynomial will have will be such that the B2k plus 1 entries are 0. Okay, I will break it. Since we know, say suppose we have n eigenvalues and they are going to occur in pairs, there could be some zeros also. So let us catch hold of that. Say suppose we have lambda 1, lambda 2, say lambda k, these are the distinct eigenvalues, or they may be with multiplicity, we will just list them all. So correspondingly we will also have minus lambda 1, minus lambda 2 and so on, minus lambda k, right. And after this, if n minus 2k is 0, then there are no 0 eigenvalues, if it is not, then you may have certain 0 eigenvalues, right. So having this in hand, what is the question that we want to show? We want to prove that the characteristic polynomial satisfies certain thing, right. So if I want to write this as a characteristic polynomial, how will I write it, right. So what will be my phi g of lambda? So this would be nothing but, since there are n minus 2k zeros appearing, Okay, so we will have lambda to the power of n minus 2k, right, into lambda minus lambda 1. Similarly, there is also an equal pairing of lambda plus lambda 1, right, lambda minus of minus lambda 1 will be there. So, there will be this factor coming across, right. If I just have to write the factors, right, and product, that is my polynomial. So, if we do this, we can see that this is nothing but lambda square minus lambda 1 square, right. So, we will have all factors sitting like this, lambda square minus lambda 2 square and so on, right. So, if we expand this, you can see that you will never have an odd term, odd power of lambda appearing at all, you will have only even powers, right. So, therefore, we can immediately see that there is no, I mean all the coefficients of the odd power term, the corresponding b case would be 0, right, all the b 2k plus 1 coefficient, all those terms would vanish. Okay. So, this implies that b 2k plus 1 is equal to 0 for every k possible, right, for every k greater than 1. Okay. So, now this completes the proof of the equivalence. Okay. So, now we will continue with what we wanted to do next. Okay. So, can we say how big my largest eigenvalue could be? Suppose I order the vertex eigenvalues in this fashion, what will be the maximum that is possible for lambda 1, or can you tell me like, okay, it has to lie somewhere between this. You can use the previous idea of the formula over here that we have presented. Oh, sorry. From here, can we conclude something about the lambda 1 value, the largest eigenvalue of the adjacency matrix? Okay, think about it, and I will not give the proof of these results, I will just give you certain bounds. Okay. So, our lambda 1 is going to be less than or equal to the maximum degree of the graph, okay, whatever we have. So, this has to be less than or equal to delta of g, okay, and in the other side it is also going to be greater than the minimum degree. Okay. So, the largest eigenvalue lies in this range between the minimum degree and maximum degree. Okay. And in fact, we can also say that yesterday we have seen this, right, about the chromatic number. So, chromatic number we know chi of g is less than or equal to delta plus 1, right. So, in similar lines we can also write chi of g is less than or equal to 1 plus lambda 1 of g, the largest eigenvalue of the matrix, right. In fact, this is kind of an insertion in between this. In fact, it need not be delta plus 1, it could be less than or equal to delta also, right, 1 plus lambda 1 of g. Okay. So, these are something about the largest eigenvalue. There are also many other results which connects this chromatic number and the eigenvalues. Okay. One more such result is that we can just see that chi of g is going to be less than or equal to, okay, this will be a kind of surprising result for you. The chromatic number of the graph is going to be bounded by 1 minus lambda 1 over lambda n of g. Okay. The largest eigenvalue and the smallest eigenvalue, you take the ratio of that, and 1 minus of that is going to be your largest chromatic number, the chromatic number of the graph. Okay. So, it is kind of the bound is, you might get surprised, how can it be 1 minus of, right. No doubts, you all accept what I say, lambda 1 by lambda n is greater than 1, yes, I did not say it is, but lambda n is going to be negative, Remember, for every positive there should be some negative, right, because trace is 0, sum of all the eigenvalues should go 0, right. As many positive eigenvalues you have, it need not be the same negative value, but sum of all positive values should be matched up with sum of all negative eigenvalues, right. So, that means what, when I arrange them in decreasing order, my lambda n will be obviously a negative number, right. So, this will be like 1 plus of that quantity whatever you have in mind, lambda 1 by lambda n, right. So, this is another interesting result. Proof is a little detailed, so I will not do the proof. If you are interested, you can go in further and look into the proofs. Okay. So, another application of this spectral, the spectrum of adjacency matrix is, or actually should I say, instead of another application, the place where it started. Okay, the energy is one concept where it started with mathematical chemists basically, when they were studying hydrocarbons and their boiling points and all those things. They ended up with in a connection between the corresponding graph structure of the compound that they are studying and the energy, that is what the boiling point energy what they have for that compound matches up with the spectrum of, there is a connection between the spectrum and the energy of these molecular compounds. Okay. So, that is one place where these spectral studies began. Okay. So, the main part is energy of a graph, which is defined after the study of boiling points of hydrocarbons basically. So, this is defined as epsilon of g is nothing but summation over lambda I in absolute value. Okay, we know summation of lambda I is 0, right, without absolute. So, you take the absolute values and add them all, that gives the energy of the graph. Okay, in absolute value you take the sum. And there are lots of studies related to this energy. Okay, we will try to cover one or two interesting facts here. So, one thing is, if the energy of a graph, okay, if it is a rational number. So, we know obviously these lambda is a real number, right. So, obviously the sum should be real number, right, because we are taking positive values, positive sum is going to be a real number. But if it happens that you have the sum to be a rational number, then the rational number is nothing but it is going to be an even integer. Okay. This is purely out of mathematical aspect, you can easily derive this. So, the theorem states that if the energy is a rational number, then it has to be an even integer. Can you see why this should be? Yes, but why should it be an integer? See, a rational, it could be an even rational, like 2 times of some rational number, it is fine, right. So, that is how the proof will go. So, if you look at it, obviously we know that if we have lambda 1, lambda 2, lambda n, you just look at the positive entries. Obviously, there is an equal negative entry because trace has to become 0. So, I can just see that if there are k positive eigenvalues, then the sum is going to be 2 times of this, right. This is clear, but why should a rational number jump into an integer? I mean, it can be rational. If energy is rational, means what? We always know sum of 2 rational numbers has to be rational, right. Obviously, there is no irrational number popping in, but it says something more stronger. It is not only just rational, it has to be an integer. Even integer you can see because of this multiple of 2 factor is there, but the claim is that it has to be in fact integer. So, it has to just do with some basic algebra. Okay, I will give you the hint here. if you look at the characteristic polynomial for this, it is going to be monic polynomial here, right, and if we have a rational root for a monic polynomial, it has to be an integer root. Okay. So, it comes from the basic algebra, you can like go back and see the algebra of equations, there it comes from the fact that just from there, okay, your characteristic polynomial, if it has, especially with integer coefficients, right, the main crux here is it is because with integer coefficients, the characteristic polynomial, it is monic with integer coefficients, right, then the roots will have to be also integer here. Okay, so, with that principle, we can just conclude immediately that the sum has to be integer and hence even. So, a little further down, how do we connect two graphs? Suppose I have two graphs G and H. If I want to talk about the eigenvalues of G and eigenvalues of H, how do I connect them? Okay, there is one way of combining the two graphs, there are various methods using like products. Okay. Usually you have seen sum of two graphs, if you have a union of two graphs you do sum and join, all those things. One other possible operation that you could do with graphs is product, right. So, the one product is called as the Cartesian product. There is a lot of studies in this field also. Okay. So, what is Cartesian product of two graphs? First of all, what is Cartesian product of two sets? Yes? Ordered pair A comma B. Yeah. So, if suppose I want to look at this, the vertex set of G cross H, in terms of graphs I will say it, you know the definition in terms of R2, R3, all those things you have studied, right, R cross R, how does it go. So, this is nothing but V of G cross V of H. So, vertex set is this, you take the two sets, take the cross product of it. So, that means what? You take a vertex from G and vertex from H, this would be the pairing that we do. So, how about the edges, how will it be connected now? E of G cross H. So, one way of doing it is, so this is where various definitions for products come into picture. Okay, so, for Cartesian product we call it also box product. So, the idea is if you have two vertices say u v and u prime v prime coming from this vertex set G cross H, you say that an edge exists between these two pairs. Now, each vertex is a pair, right, each vertex is a two tuple. So, an edge exists if either u is equal to u prime and v is adjacent to v prime, that is v prime belongs to the edge set E of in H, or u prime belongs to edge E of H and v is equal to v prime, right. So, this is the condition that we put. So, now with this condition, if I want to look at it, suppose I know the eigenvalue of G and spectrum of G and spectrum of H, what can I say about the spectrum of this product graph? Edge set of G and v is equal to v prime, right. So, suppose I just start with the condition that we are looking for, spectrum of G is say lambda 1, lambda 2, lambda n, say on n vertices. So, I did not define all those things, G is on n vertices, H is on m vertices we can take, right, and say spectrum of H is say mu 1, mu 2, mu m. Then what can we say about the spectrum of G cross H? Okay, I will tell you that. So, spectrum of G cross H is going to be nothing but, anybody? Any guesses? So, obviously how many elements are going to be there? vertex set contains how many elements here? M into n elements, right? If there are n elements in G, m elements in H, then G cross H has mn vertices, right? So, the number of elements is m into n here, right? So, we should have m into n spectral values, right? Eigenvalues are there. So, what would be that? Okay. So, the eigenvalues take this very special pattern. So, where I is lying between 1 and n and j is lying between 1 and m. It is nothing but all possible sums of the eigenvalues from both the set, lambda 1 plus mu 1, lambda 1 plus mu 2 and so on. Similarly, you take lambda 2 plus mu 1 and so on. So, all possible sums are going to be there here, that is taken one from spectrum of G and one from spectrum of H. Okay. So, these properties actually give us a way to construct higher order graphs also, higher order networks. In the, when we go in for networking analysis, we can do this from here also. So, is it kind of going above your head already? Yes. So, now okay, we will get down and we will start from again from the basis. Okay. So, now let us talk about another class of matrices. Okay. So, I wanted to talk about Laplacian matrix. Okay. So, I will give you the definition of Laplacian matrix and then we will digress and we will come back to Laplacian, because I want to connect two different matrices here. Okay. So, Laplacian, by the word suggests, you have heard this Laplacian word in differential equations, right? Whenever you study about differential operators and other places, of course, here also there is a role for Laplace. Okay. So, Laplacian matrix is defined as, say suppose I have the graph G, L of G is nothing but 1 if I is adjacent to, sorry, minus 1 if I is adjacent to J, okay, and 0 if I is not adjacent to J, and of course, I not equal to J. Let us now concentrate about simple graphs, right, and the diagonal entries, if I is equal to J, then it is nothing but the degree of the vertex, okay, say d of the vertex Vi. So, what do we have? So, V of G has the vertices, say V1, V2, Vn. So, obviously, L is a Laplacian, L is an n by n matrix. Okay. So, what else can we observe from here? If we have an undirected graph, can you see that L is symmetric again? Right, wherever you have adjacency, you are going to replace it by minus 1, right. So, far I am not talking about direction here. For directed graph, we have a different definition. So, for time being, we will again stick to undirected graph. Okay. Okay. So, there is also an alternate way of defining this Laplacian. By the way we have defined it, this L of G is also nothing but the degree matrix, where the matrix contains, it is a diagonal matrix with the diagonal entries are nothing but the degree of the vertices, okay, in the corresponding order, right, minus the adjacency matrix. Okay. So, if I give this definition, then it will be clear for you why I wrote that first. Okay. So, it is just to make you feel for the entries here. So, one thing what we immediately observe is L is symmetric, right, and any other observation that we can make? Determinant is 0. So, always your, why is it 0? So, row sum and column sum, if you look at it, row sum of L is equal to 0 for any row sum, and column sums are 0. So, obviously, we expect the graph to the matrix to be a singular matrix, right. So, determinant becomes 0. So, any other thing? Can we just pull it out from here? Trace is 2m. So, trace is nothing but number of edges, twice the number. Why is it 2m? Sum of the degrees is twice the number of edges, I am sorry, right. Anything else? At the first go, can you observe anything else? Okay, so to further in this direction, let me go about to another matrix and then we will come back to this, okay, so that you will know, you will be able to appreciate much more easily.